Good morning, everyone. Welcome to the Daily Math Challenge. We're going to look at Cartesian planes, coordinates, all that stuff today. So let's get started. So the first question, we asked to plot coordinates. 4 coordinates here: 2, 3, minus 2, 5, minus 1, minus 3, 4, minus 5. And we're given a Cartesian plane below to plot them on. So this is what I'm going to do. Okay, I'm just going to screenshot that and bring it up because I can annotate it in front of you. So let me do that. Okay, there we go, that'll be better. Okay, so let me just have, sorry guys, there we go. So I have my coordinates I'm going to plot here, and I have the axis here. So I'm going to go ahead and, sorry, I'm actually just getting my annotator out. Okay, so for 2, 3, basically coordinates are a way to explain where on what's called the Cartesian plane, that's this flat surface here, we're at. Now this Cartesian plane isn't just this big, it goes on forever. Just because we've gone up to 6 here and 6 here, it actually goes on forever. Just think of these two things as number lines. The first number of the in the coordinates is telling you how far along this number line we are. So 2 is saying we're here along this number line here. We're at 2. Remember, x comes before y in the alphabet. The same is the case with these ones. This is the x coordinate, this is the y coordinate. It tells us where on the x-axis and y-axis respectively we are. So 2 tells us we're here on this number line. 3 tells us that we're here on this number line. So we're here on this number line, but we're also here. So that tells us we're going to be here. So that is 2, 3. Now for minus 2, 5, the first number is actually minus 2. So if we look on this axis, where is minus 2? Well, it's here in this number line. And 5 on the other number line is all the way up here. Okay, so that means we have to be here. Okay, and minus 1, minus 3, that's telling me that we're at minus 1, minus 3 here in the same sort of way. And 4 minus 5, well, 4 is all the way here, and then minus 5, you go down to here. So there we go. Okay, so let me just get my annotator off for you, and we can go, well, how do I do this again? There we go. Okay, now let's go back to, the dots are still there. I'll get rid of this in a second. Actually, we're going to need them to do the next question. So let's just go over to the next question. So the next question says, if I just, actually, what would I do? Yeah, let me just move this away for a second. What is the distance between the points 2, 3, and 4, minus 5? 2, 3, and 4, minus 5. Let me just put this back where it was. Gosh, this is going to be a task now. There we go. I think it was there. Okay. So 2, 3, and 4, minus 5. What is? These are the points we've already plotted. Now, what is the distance between these two? So let me get my annotator back on. There we go. So when we talk about the distance between 2 points, it's literally like, this is a flat surface. Imagine that you have a ruler, and each on the axis, and they should be to like the same length, right? Let's pretend each one is along as 1 unit. So this could be 1 centimeter, 1 meter. It depends on what unit you want, but we're just going to call them units. Okay. And then I don't even know if you can draw a straight line on this thing, but imagine drawing a straight line from there to there, and we measure that line. That's the distance between these 2 points. Now we can use triangle theory to help us work out this distance, because if we draw a horizontal line from this point to above where the other point is, and then we go down, we've actually created a right angle triangle. Remember, axes, they are perpendicular to us. There's a right angle here. So that basically sets us up so that if we do that, if we go across and down, we can have a right angle here. And it's very easy to measure these lengths because we can just look at the number line below and see how long that is just by measuring it up against it. So let's go down. This is so crude, but it works. Okay, so this is 1, 2 along. So we say this is 2 units long, this side. And this side here is 1, 2, 3, 4, 5, 6, 7, 8. 8 units long. Okay. And then what we're going to do, I actually might change right now to my paper, but we're going to use what's called Pythagoras' theorem. That gives us the length of this long side here when you know the 2 shorter sides, the sides that are next to this right angle. So that's what we're going to do now. Let me just get rid of all that sketch and go back to annotator. There we go. Okay, so where am I? There I am. Okay, let's get back to this. So Pythagoras' theorem says that this length here, let's say x is equal to the square root of 2 squared plus a squared. And I know what you're saying. Technically, you know, Pythagoras' theorem says the a squared plus b squared equals c squared, you know, right angle triangle stuff. Yeah, that's true. I've just slightly rearranged that equation. So yeah, let's see what we get. So we get that x is equal to the square root of 4 plus 64. So basically the square root of 68. I'm not going to be all slick and work that out by hand. I'm just going to type it in the calculator here. Square root of 68. Let's see what we get. 2 root 7. Okay, this button here, S to D, basically changes the form of the answer. So I want that to be in a nice decimal. There we go. 8.25 to 2 decimal places. 8.25 units to 2 decimal places. Alright, so we've got that. Now what did I want to tell you? Okay, I think I'm also going to show you another way of this. Let me just remind myself of the points 2, 3 and 4 minus 5. So we wanted to find the distance between these 2 points, right? So this is another formula you can use, okay? And it's the same idea. So x1, y1, x2, y2, let's just label those. And actually the distance between these 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared. Now the reason why is really, it should be clear from earlier, but just look back at it if you will. 2, here we go. This was actually, if you think about it, we went down to the x-axis and we did x2 take away x1, right? x2 take away x1, that was 2. So let's do that. x2 is 4. x1 is 2. Square that. So we get 2 squared. That was my, this part here, 2 squared. And then we did the, this length was, if we went to the y-axis, the y-axis was over here somewhere, right? And so so this was y1, this was y2. The distance between them is y2 take away y1. So y2 take away y1 is minus 5 take away 3. I know it looks weird with negative numbers being associated with distance, but it's fine. It's just the magnitude of that number, ignoring the sign, that's the length. It is 8 units down. The minus is just telling us that we're going down from this point to this point, okay? So you don't need to get worried about that. In fact, the minus number will disappear when you square it earlier, okay? I mean, we did that earlier. So you get the same answer if you keep going. You get the square root of 2 squared plus 8 squared, and then, you know, you just keep going. So that was that answer. That was that question. I don't think there's anything else I want to go through on that one. But yeah, Pythagoras' theorem, definitely you need to know that and also do these questions. I would encourage you to revise that if that's what you're stuck on. Okay, so let's go to goals. What is the name of the shape formed by the collection of points x, y on the plane, where x squared plus y squared equals 1? So let me do this part first. Now, oh gosh, let me get rid of that. Don't want to give away the surprise. So here we have a, sorry, let me just get rid of that. Maybe I can, there we go. So here we have, I'm on Desmos. It's a really good graphing calculator. I typed in here, let me just do this again. I typed in the formula x squared plus y squared equals 1. And how I did those squares, I just did shift 6 and then I typed in 2 and then I pressed space. And that gave me those indices, okay? Easy peasy. So you can see that this circle, right? It's a circle. So that's what you get when you plot this graph. And what this graph is, it's a collection of points x, y. Let me just write this stuff down. So when we plot this equation, what we're doing is we look at every single coordinate. Imagine x, y, we just have a random one we've chosen. Obviously this could have been anything, so I'm not going to say it's a particular number. It could have been anything, so I'm going to leave this general and say it's x and y. Whatever the x coordinate is, that's that. Whatever the y coordinate is, that's that. And what we did is we thought, okay, do we colour this in or not? We have this rule here, this equation. We want to plot it. So I'm looking at every single point on the Cartesian plane, that flat piece of surface. There are infinitely many of those. And I'm going to see if each point actually satisfies this equation. And if it does, I'm going to plot it. So let's look at a few coordinates that satisfy this. Let's say when x is 1 and y is 0, x squared plus y squared, is that equal to 1? Yeah, 1 plus 0 is 1, so 1 equals 1. That gives a true equation. So this gives a true equation in this case. It is true that x squared plus y squared equals 1 in this case. So we plot 1, 0. And where is 1, 0? It's here, 1, 0. Can you see? So we plotted that one, and everything is right with the world. Okay, you can do the same thing with this one. Okay, we check if that is on the thing. I'm so sophisticated. The Cartesian plane. Memory went there. Okay, so we do that, and everything's fine. I'm gonna do one other one just for fun, you know. 1 over square root 2, 1 over square root 2. I'm not going to go into depth into how you work with square roots yet. But so when you plug this into your equation, you actually get that this is equal to a half plus a half, which is 1. And that is equal to 1. That's good. Now what about the point 2, 1? Well, 2 squared plus 1 squared equals 4 plus 1 is 5. Gosh, that's terrible, isn't it? That's not equal to 1. So actually, we don't plot this graph, this point 2, 1. And can you see? 2, 1, where is it? It's over here, missing out on all the fun. So that is not in our circle of friends. I'm sorry for inflicting that joke on you. But yeah, who would have thought it? I make dad jokes without even being a dad yet. Okay, let's move on. So, okay, the question says, where is that thing gone? There we go. So we need to do this now. So are there any solutions to the equation x squared plus y squared equals 1 and y equals minus x plus square root of 2? And what is going on graphically here? So it's asking us, first of all, if there are any solutions to this equation. So what I'm going to do, I've written these here. So remember, solutions to these simultaneous equations mean you're looking for a coordinate x, y, so that if you were to put them into each equation, it would satisfy the equations. So you would come up with a true equation. So x squared plus y squared really would be 1, and y really would be minus x plus square root of 2. So are there any such numbers, x, y, and x, where that satisfies both? Well, with simultaneous equations, it's not always the case that you get a solution. Okay, sometimes you get 1, sometimes you get infinitely many, sometimes you get none. So we need to work out what's going to happen. I'm going to look at algebra first of all. I think I'm going to do it this way because it'll be more satisfying when you see graphically what's going on and how we have the marriage between the visual aspect of the the graph that we were plotting earlier, and actually the algebraic concepts of when you have solutions to equations. I love that link. It's just like satisfying. So hang on there. It is going to be good. Just bear with me. So so let's think about how we would solve this. So I know if let's pretend I found a solution. Now it might not exist, in which case later on the road we'll get a crazy conclusion like 2 equals 1, where maths falls apart and we get a contradiction. So it would have turned out that there wasn't a solution to begin with, and our assumption was false. But let's just assume for now that there is a solution, and let's see what it would be. Okay, so if x, y is a solution to both of these, I can replace wherever I see y in this equation, I can replace it with minus x plus root 2, right? If x squared plus y squared is 1 and y is this, then I can just replace x squared plus y squared with this y here, this whole expression, and it's still going to be 1 because y is the same as this. So let's see how that will go. X squared plus minus x plus root 2 squared equals 1. Now I'm going to get x squared plus x squared minus 2 root 2 x plus 2 equals 1. I'm not going to explain how I got that. I'm going to take away 1 from both sides. That's going to give me this equation, and then let's tidy it up. 2x squared minus 2 root 2 x plus 1 equals 0. And the way we solve that is through quadratic equation. So I'm not going to go into that either because that's just a whole kind of worms. And I don't want to leave you guys in tears because it is not something that's fun to jump into straight away without doing the necessary kind of foundational work. Okay, so x equals minus b plus or minus the square root of b squared, that's going to be b squared minus 4ac, so minus 8. Yes, that's right, that's what I'm expecting to happen. All over 2a. Now, this is going to be 2 root 2 plus or minus the square root of 0 is just 0 plus or minus 0 over 4, okay? And that's going to give me just one number, 1 over root 2. So guys, and I'm thinking particularly of GCSE students who would have come across this, and A-level students, remember whenever you have this guy here, this bad boy, the discriminant, whenever that's 0, it means that you only have one solution. If this was negative inside here, you would have no solutions because you can't take the square root of a negative number. There's no number that squares to give a negative number, so there will be no real number that will satisfy it. And if this discriminant is non-zero, then you have two different numbers corresponding to you plussing or taking away a non-zero number to get the two different values of x. Remember, plus or minus is basically saying we have two different numbers here. I'm giving you that x could be. One is where you take this symbol as the plus, and the other route would be when you take the this symbol to be the negative. So why it's called plus or minus. And there's only one solution, so that tells us there's going to be if you think about these what we had, these simultaneous equations. If I plotted both of these on the graph, all the values of all the coordinates x, y, where if you plug it into here it's going to be true, and if you plug it into here it's going to be true. If you plot both of those graphs on at the same time, they should intersect at one point. Because remember, the solutions to simultaneous equations are precisely the points where that are on both curves at the same time, which is the case when they intersect. So we're expecting, because there's only one solution, when x is 1 over root 2, and actually when y is 1 over root 2 as well, you'll see that later, there's only going to be one solution, one place where they intersect. So let's see this, okay, let's see this. Let me go to, well, I actually had this equation, the same equation we had earlier, up, and I'm going to plot that. Can you see? It's intersected at, that is 1 over root 2, 1 over root 2. It's just they've given the decimal version, but so this is the only place where it intersects. And for a circle and a line to intersect once, basically the line has to be a tangent to the circle, so it just means that it touches it once. It doesn't go, if it was anywhere below this line, it would touch it in two different places, and there would be two solutions, okay? And that would have corresponded to the situation when the discriminant would have been earlier, would have been non-zero. And if the line had been a bit up, can you see that this line here wouldn't have touched at all the circle, which means that actually there would have been no solutions, and that discriminant would have been negative, the number inside the square root, giving us no solutions. So yeah, guys, that was today. Let me see if there are any more questions. Yeah, I've already explained what graphically is going on. But isn't that satisfying? The idea that the fact that when we did the algebra and we had that x only had one, the xy only had, like, I'm not speaking very well. The simultaneous equations only had one solution, algebraically. We then go over to the graph, and lo and behold, it only touches it once. And I love that fact. I just love it when in maths different things line up and they agree. There's consistency. It's so beautiful. That's what truth is all about, isn't it? Just when things working together well, and complementing each other, and seeing truth manifest in different ways in different spaces, like in the Cartesian plane or algebra. It's beautiful. Okay, guys, I'm going to leave you there. I want to encourage you to, if you found this hard, you know what, this goes with all my videos that I've been going on about all the topics of maths we covered, and it actually in maths, all of maths in general, everyone can do maths. Honestly, like when I look back on my journey, I'll probably talk about it a bit more in the future, but all it takes is determination and just not giving up, laying your foundations well, just not skipping steps when you do questions, testing your understanding by doing questions, and really working on problem solving questions in each of the math topics that you come across, you know, like, and as long as you have like a good textbook or a good resource to read that takes you through all of these things, you'll be onto a winner. Like graphs aren't complicated. You know, sometimes there are mysteries and sometimes it's confusing, like why does this work, or what does it mean to plot a graph or whatever. But remember, like, when we say plot a graph, there's so many ideas and concepts that are in our mathematicians' heads behind the scenes that we've already kind of implicitly agreed upon. And it can be quite confusing when you read a textbook to kind of work out what's going on here. But you just have to read between the lines, try and work out what's going on. If you persevere, it will click. Trust me. And remember, you can always use questions as a way to test whether or not you've understood a concept, because they're designed to tease out any area of misunderstanding you have, any area of ignorance you have in terms of these things. So mistakes are your friends. They point you in the right direction. Okay. Many things I can say to this, but honestly, guys, the journey of doing maths is such a satisfying journey. It trains your brain. It's so satisfying when you overcome challenges, and it's like so lovely to have a problem to work on where it's very self-contained. Like, you know, like the world of mathematics, it's like the world of abstract ideas and all these things that we've built from numbers and, you know, functions and stuff like that. Like, it's a self-contained world, really, where you can play around with it and solve problems that actually can translate into you taking your brain up a level and just stretching it. I could waffle for a long time, so I'm going to spare you, but thank you for listening. Yeah, definitely would encourage you to do these questions, but I don't know why I'm saying this, because if you're this far, you probably would have done them already. Anywho, I love you and leave you. See you next time. Alright, thank you, bye. If I can find this button to switch off, there it is.